In the previous video, we looked at what linearization is and how to find the linearization of a line at a given point. In this video, we'll look at the application of linearization. That is, we're going to use the linearization of a curve to approximate the y value of a nearby x value. Let's look at an example of how we can do this. Let's say we want to approximate the square root of 123 by using the linearization of f of x equals the square root of x at x equals 121. We can use the point slope formula with a little bit of calculus thrown in. That would be y minus f of a is equal to f prime of a times x minus a. In this problem, we have a few numbers that were given. We have the square root of 123, and we have x is equal to 121. X equals 121, this is our value of a, or the x1. And this square root of 123, this is what we plug into the linearized equation once that's been found. We don't actually plug in the square root of 123. Instead, we're only going to plug in 123. That's because the linearized equation was for the square root. So to do the approximation, we only need the number inside of the square root. We know our value of a is 121. So let's erase all the a's and replace those with 121. Next, we can find f of 121 by substituting 121 into the f of x formula. The square root of 121 is 11. Now we need to find f prime of x. This would equal 1 over 2 root x. Finally, we can find f prime of 121 by plugging 121 into the f prime formula. This would equal 1 divided by 22. Inside the equation of our line, let's go ahead and erase f of 121 and replace that with 11. We could also erase f prime of 121 and replace that with 1 over 22. Let's simplify this formula and solve for y. First, we can distribute 1 over 22 into the parentheses. Then we can add 11 to both sides of the equation. That'll get y by itself. We need a common denominator to combine the negative 121 over 22 with the 11. This would give us negative 121 over 22 plus 242 over 22. And so our y-intercept for this would be 121 over 22. Now that we have the linearization of the square root of x, we can plug in our value 123, which will give us an approximation for the square root of 123. We substitute 123 into our linearized equation. This would give us 244 divided by 22. Written as a decimal, this would be 11.09 repeating. And keep in mind, what we just found was an estimate for the square root of 123. The actual value of the square root of 123 is not a rational number. We can round this value to 11.0905. So our estimate here was actually pretty good. Our estimate was within 0.0004 of the actual value. And since the estimate was higher than the actual value, we would call our estimate an overestimate. Showing whether your estimate is an overestimate or an underestimate is actually pretty important. So important that the College Board actually has a standard for this. Standard CHA-3.F.2 says, for a tangent line approximation, the function's behavior near the point of tangency may determine whether a tangent line value is an underestimate or an overestimate of the corresponding function value. The key takeaway here is that using a tan line to approximate a value, you'll either end up with an underestimate or an overestimate, unless the function itself was linear. The way that we can tell if our estimate is going to be an overestimate or an underestimate at a point without calculating the actual value is determined by the concavity of the function at that point. Let's consider a parabola, which is either concave everywhere if the coefficient of the x squared term is positive, or it's convex everywhere if the coefficient of the x squared term is negative. Since this parabola is concave, the tangent line is going to exist below the parabola everywhere except for the point of tangency itself. As the distance between the point of tangency and the point that we're trying to estimate gets bigger, in this case our estimate gets worse and worse. And as it gets smaller, the estimate gets better and better. So now let's consider if the parabola opens downwards. This would be convex everywhere. The tangent line in this case would exist above the parabola, except at the point of tangency. And this is true no matter where on the parabola you look. The red dot, which is our estimate, is always going to be above the black dot, which is our actual value. So this would be an overestimate. If you look in the description of this video, I've left a link of this example in Desmos so that you can go in there and play with these sliders yourself. The slider S will change the concavity. If S is positive, it will be concave. If S is negative, it's convex. The slider A controls the point of tangency, and the slider D controls the distance of your estimate from the point of tangency. So what did we just learn from that exploration? If our graph is concave at x equals a, then the tangent line will exist below the graph in that immediate area. If the graph is concave at x equals a, then the linearization will be an underestimate. How do we know that a graph is concave? We know by looking at the second derivative. If f double prime of a is greater than 0, that means that the graph is concave at a. And what we mean specifically by underestimate is that the estimated y value is less than the actual y value. On the flip side, if our graph is convex at a point, that means the tangent line will exist above the graph in that immediate area. If the graph is convex at x equals a, then the linearization will be an overestimate. How do we know that a graph is convex? Look at the second derivative. If f double prime at a is less than 0, that means that the graph is convex at x equals a. And that word overestimate just means that the estimated y value is greater than the actual y value. Let's consider the example that we used before, where we approximated the square root of 123 by using the linearization of f of x equals the square root of x at x equals 121. We determined that this was an overestimate by comparing the actual value to the estimated value. The function we were given was f of x equals the square root of x, and we were using x equals 121 to do the linearization. We already found that f prime of x was equal to 1 over 2 root x. Since we now need to find f double prime of x, I'm going to go ahead and write this as a rational exponent. F double prime of x would then be 1/2 times negative 1/2 times x to the negative 3/2, and this would simplify to negative 1 over 4 root x cubed. Now we can plug x equals 121 into the second derivative formula. That would give us negative 1 over 4 times the square root of 121 cubed. This would be negative 1 over 4 times 11 cubed, which ends up being negative 0.00019. All that really matters here is if our answer is positive or negative. In this case, it's negative. It's less than 0. Since f double prime of 121 is less than 0, that means that we have an overestimate. And that's all there is to linearization. So to sum up, linearization just uses the equation of the tangent line at a point x equals a to approximate a y value near x equals a. And once you have your linearization formula, you can tell if it's going to be an overestimate or an underestimate by looking at the concavity at that point. If your graph is concave at that point, that means that you're going to have an underestimate. If your graph is convex at that point, that means you're going to have an overestimate.